Hi, my name is Cassandre Galliard, and I'm going to present you today a part of my PhD, which is on the assessment of alkali-activated slag carbonation. So first, the durability, the ability of materials to last without repairs, and there are different kinds of attacks, physical and chemical, which can lower the durability of materials and cementitious materials. Here you can see that for cementitious materials, carbonation and chloride attacks are causing a reinforcement, the corrosion of the reinforced steel in the reinforced structure, which is an issue. The carbonation is a reaction of the CO2 with the materials. And for cementitious materials, carbonation is one of the main issues because contrary to most of the materials, it's present almost everywhere, as you can see, because of the carbon dioxide that you have in the atmosphere. The carbonation is happening in 3 steps. The first step is the diffusion of the CO2 in the materials. The second step is the dissolution of the materials within the pore structure. And the third step is the carbonation of the main phases. And for alkali-activated materials, it's the decalcification of the Cash phases and Nash phases, so of the gel phases. And you can see here that what we call the carbonation front is where the pH change drop. We call it the carbonation front, and it's really important because it is when the steel bar can be corroded and is not protected anymore by the high pH. So that's what we want to avoid. But for alkali-activated materials, carbonation can also be an issue because if the Cash and Nash phases are decalcified, they can lower the mechanical properties of the materials, which we want to avoid. To have a better understanding of the carbonation of alkali-activated materials, I decided to use this mix design and to let, so it's a cement paste, and to let different set of cube in 4 different environments. The first one in outdoor, but protected from the rain. The second one outdoor, but exposed to the weather. And the 2 last one in the cement lab and in the 20-degree climate chamber, where the relative humidity is relatively low. The sample that were outside had a high relative humidity because it was during the winter months, so November, December, and January in United Kingdom, so it was raining a lot and the relative humidity was really high. After 3 months of carbonation, the sample looked like this once open. You can see that there are different colors. This is due of the oxidation of the sulfur. It's a mechanism well known because of this stone, the lapis lazuli stone. And you can see, for example, in the laboratory picture that there are red, green-ish, which is one form of sulfur. And after you have this green-blue, which is another oxidation state of the sulfur. And you can see also a white part and also a white, green, gray part for the sample inside. And for the sample outside, we can observe only this white part, which is really low. It didn't went that far. This is mainly due to the relative humidity, which were really high outside and low inside. And also we had some crack within the sample due to the drying shrinkage, due to the low humidity, low relative humidity. So that's why the air was able to penetrate that far. We can assume, but we're not sure, but we can assume that maybe the carbonation front is equal to the change of color front, to the oxidation front, because the CO2 can go as far as oxygen. But after doing this phenolphthalein test, we can see that actually the carbonation front doesn't look like the oxidation front. So phenolphthalein is a molecule that is colorless when the pH is below 9. So the samples are all pink, which is different for Portland cement system, which will be colorless when it's carbonated. But we can see here, we can see a different shade of pink. We can see a lighter shade of pink, which is due to a lower pH, but probably a pH above 9, which is in agreement with previous study. And we can see that for the sample outside, the carbonation front seems to be the same than the oxidation front, even though it's really hard to tell because of the dark color of the sample. And for the sample inside, we can see that the carbonation front seems to be equal to the dark gray light area, white area, not dark, light gray area. But to confirm this, I did some thermogravimetry mass spectroscopy analysis. So we cannot draw a conclusion out of the oxygen mass spectroscopy, but we can see that there are 3 main peaks. The first peak is due to the water loss within the gel phases. The second peak is due to the hydroxide water loss, and the third peak aragonite or vaterite, and the third peak calcite, which is the less and the more stable form of calcium carbonate. The main difference between the sample outside protecting from the rain and the sample outside exposed to the rain are the fact that we cannot find aragonite, or not that much aragonite or vaterite, which is probably due because the sample had the time to carbonate properly, whereas for the sample exposed to the rain, there was too much water. And we can see that the peak of water within the carbonated part, the white part, was really high, which is probably due to the free water within the sample, while for the sample outside under the shelf, the water loss due to the cache phase is lower, which is probably because the calcium, the cache has been decalcified by the carbon dioxide. For the sample inside, the main difference is that we have almost no calcite, but a lot of aragonite or vaterite. And we can observe the same process for the cache phase, so the carbonated part has a lower amount of cache phases. To confirm this, I did some XRG analysis, and it confirms that there are some calcite and vaterite, but not aragonite within the carbonated part, and also that the cache phase is almost not there, so the cache phase is the bomb there, and it's almost not here anymore when it's carbonated, so it confirms the TGMS results. I did also some SEM analysis, and we can observe that for the sample was protecting from the rain, actually the oxidation front, which is there, is slightly different from the carbonation front, and the carbonation front seems to be pretty big, actually. After zooming in this image, we can observe that the carbonation part has some pore dropping and a lot of crystal, which is probably calcite or vaterite. And we can observe also white dashes within the carbonation front part, which is weird. So I did some ADX elemental maps, and we can observe that these white dashes are actually high calcium molecule, but we don't know yet what it is. It needs to have more analysis. For the sample exposed to the rain, the carbonation front is really sharp, but is there. And we can see that even if it's less carbonated in the lab and in this chamber, it's still carbonated, and you can still see the pore dropping. So the conclusion are that the cash gel lower during the carbonation, while the calcite and vaterite increase, and that within the carbonation front, the calcium is really high. Also, we can see that the pH is lower when the carbonation happen, but less than for Portland cementitious materials, which is really good because it means that it will it might not be an issue for the steel reinforcement. And finally, we can see that the oxidation front is different than the carbonation front. So thank you all for listening, and thank you to Dan Geddes, Brian Walkley, and John Provis, and all the cement team of Sheffield for the help. If you have any question, please ask it.